Hello, this is Brock Skaggs, and I'm going to make this video as a companion video to one I've already made. And so that companion video, you can see some of the work of it on the screen now. Basically, it went through a velocity analysis of a simple four-bar mechanism, specifically a crank rocker mechanism, where we knew the angular velocity of the crank at a given instant in time, and we're trying to figure out the angular velocity of the rocker at that same instant in time. And so there we did it as a very analytical exercise. Basically, we went through and we analyzed the coupler, picked out a couple points on it that would be of interest to us, and basically went through a relative velocity approach in order to determine the magnitudes of a couple velocity vectors. Specifically, the one that we were after was the linear velocity of this point C. Because after we knew the magnitude of the linear velocity of point C, we were able to relate it back to the angular velocity of link 4 here, with points C and D at its endpoints. And so I want to go through a same problem, except for now using a graphical approach. And what the graphical approach is nice about is that all this angle work here, specifically where I'm trying to determine how to write these vectors with unknown magnitudes, how to write them in I and J components, a lot of that we can basically use CAD tools in order to take care of for us. Also in here we wrote a vector equation, and then we wrote basically the same equation just looking at the I and J components, and we solved a system using Sage Math Cloud in order to help us work through the math there. Well, basically instead of doing that, we'll basically think about tip-to-tail graphical addition and how this should work out in order to determine the magnitudes. And then just after we've drawn our vector triangle in this case, then we can just measure side lengths of it in order to come up with the correct values. And so that'll be the idea for this video. And so I'll switch back over here now to the graphical version. Same problem statement here. First part of the work is really still the same. We've got to figure out what points we need to determine the velocities of in order to solve the problem. And so of course they're the same as the ones before. The one change I'm going to make here is that I do need to still make a calculation in order to determine the linear velocity of point B. And so we ended up last time with 6 pi inches per second. But I can't really type in 6 pi into AutoCAD to define the length of a line, and so I just need to figure out what the decimal equivalent for that is. And so here, 6 times pi in my calculator, I'm just going to take it out to 2 decimal places, 18.85 inches per second here. And so I'll go ahead and make the note here on the screen that 6 pi inches per second is approximately 18.85 inches per second. So with that, now we can start going into the CAD side of things. And so one of the things I have over here in CAD is the AutoCAD drawing that I use to just lay out the mechanism for the picture at the beginning of each of these videos. But I don't really want to work on it. I want to make a similar drawing to this right here to begin with. And so each of my links is just represented by a line here. And so I'll just play off of what I already have. And so here I'll draw a line from A to B. There we go. And I'll just move this off now. Just using the move tool inside of AutoCAD here to preserve the direction. So I'll move it way off here until we'll have our simplified sketch here. Here is the line associated with the coupler BC, just with that center line type. And so I'll just copy it and connect it here. Go ahead and convert it over to the solid visible layer at this point. And then finally we've got the rocker here on the right hand side, and so we'll draw a line to represent it as well. Turn off ortho snap here. There we go. Having to be careful on those donuts to make sure that I get the exact center of it. And then we'll move this line as well. And really I need the bottom edge of that because this is where the pin connection is. And so this should be it. I'll go ahead and copy a few of these letters just so we can make sense of it with respect to the other one. This is A. We'll have B up here, C, and D here. So B, C, and D. Alright, so there is the line drawing, if you will, very simplified, of our crank rocker in this exact position we're talking about with respect to time. And so now I need to start thinking of the vector equation. This vector equation, the velocity of c is equal to velocity of v, velocity of b plus c relative to b. And so the one vector I know everything about is the velocity of b. I know that it's 18.5 inches per second for the magnitude, so that would be the length of our line. And also we know the direction. The direction has to be perpendicular to the line representing the crank. And so here's the line representing the crank. It needs to be perpendicular. Also, it needs to be pointed up and to the left, just because we know it has to agree with the angular velocity of the crank. And so what I've done here is I've created two layers, a vector underscore known layer and a vector underscore unknown layer here. And so I'll go to my known vector layer. I'll hit L enter to get the line going. First, I'm just going to draw a little stub line for the direction, and then I'll get a line tool going again. Here I'll use the parallel tool, and so I'll wait till it snaps there. I've got the locator. Now it's going to run a line parallel to that perpendicular line. So this line should be exactly perpendicular to line segment AB there. And so this line is going to represent that vector velocity of B. And so we said that had a magnitude of 18.85. And so entering that into AutoCAD and hitting Z enter allows me to create my first line here. And that red line is the vector VB. And so here what I'll do is go ahead and make a little arrowhead here. Let's just say it's 1.5 length for the head, 30 inches there for that angle, and I'll mirror it across here. The reason I'm doing this is just to keep track of which end's the start end and which end's the terminal end of the vector. And so here is the V sub B. And let's go ahead and move it off of this diagram. Here, just resetting the zoom so I can work a little better. And so here's my velocity vector. I'll try to move it down here so we don't get into the other work. It's also handy to go ahead and label these just in case you get into more complex vector style problems, which will come with acceleration graphical approaches. And so here I have a nice label saying, hey, this is the velocity of B here. And so going back to our vector equation, basically we've taken care of V sub B. And so let's work on the right hand side first. And so we'd basically be doing tip to tail addition, and we'd have velocity of C relative to B next. And so we know velocity of C relative to B needs to be perpendicular to the line representing the coupler, but we don't know the magnitude yet, so we can't really draw the length of the line up to this point. And so we can handle this one way by drawing a line, and here I'm going to put it on a different layer. I'll put it on the vector unknown layer, and here I assumed it was going to go in the downward and left direction, and so I'll just use my snap to perpendicular here, let it pick up that line, and then just extend a line out here. Again, I don't know the length of it yet, so I'll just make it fairly long and come to this point here. And here, just to not have to worry about line tape scale, we'll go ahead and make this green. And so all the green vectors will be unknown. And so here I don't know the length of it. Really, it could also go in the opposite direction. But I do know the direction is right, as far as it's going to lie somewhere along that line as far as the representation for that relative velocity vector. I also know that we're basically going to play vector addition here on the right side of this equation. And so this needs to be tip to tail addition. And so I'll just type M enter to move, and then I'll select this line, and I'm going to bring it down here to my V sub B. and place it right at the tip of the arrowhead. And so now I really do have this tip to tail addition going. And so that takes care of C relative to B for the moment. And now we've got to work on the velocity of C. And so again, you think of the velocity of C. I don't know the magnitude yet, but I do know direction. And so the direction is known because it has to be perpendicular to the line representing the rocker. And so I've got the rocker defined, so I just need to draw a line very similar to the way I did for VC relative to B, except for now my reference is the rocker. And so here is the rocker, and I'll go L enter. We're still on the vector unknown layer. I'll go snap to perpendicular, and I'll just drag this out to some unknown length there. And this needs to be the resultant of the vector addition on the right hand side. And so when I go to drag this down here to form my vector triangle, I need to start it right here at the start point of the VB vector, and then I'll be looking for the intersection of the two lines that are green. And if I zoom in close enough, you can see they're dashed as well. And so when I move it here, I'm moving it to the endpoint, you can see, of the first vector I drew, the red v sub b. And really, by looking at the intersection, I'm looking at the solution to that vector equation. One thing to note here, I did assume the right directions for both of these. That's why they intersected here. But if you happen to not assume the correct direction, basically you'll end up with something that keeps extending off and not ever meeting together. Examples here, if I would have picked this one to go in the upper to the right here, you would have been able to say, hey, if I drag these things off to the right, they're just going to keep getting farther and farther apart here. And so then I would have known, hey, one of them at least is in the incorrect direction, flipped it in order to find the intersection. But with these unknown magnitudes, basically you're looking for the intersection of these two vector lines. At this point, after I've got the intersection, I can just do a quick trim operation here. Let's go ahead and put in the arrowheads for them. This line on top was the relative vector, C relative to B. And so here I'll just come in. What is the angle? 23, so let's go 53 there. And draw my arrowhead here. And so this would be velocity C relative to V. Let's go ahead and copy this so we can have a label. And let's put that on the green layer here. And the second one is the velocity of C. And there's our label here. It's starting here at the beginning of our red vector, and it's going to end over here somewhere. And so we'll go ahead and draw the arrowhead on here just for completeness as well. Let's say a 50-degree angle there is fine. And we'll mirror it across. And so now I've basically done the equivalent of solving my system of equations. I have already obtained the magnitudes of the two vectors. Now it's just a matter of measuring the lengths of the lines. And so here I'll be sure to grab a line dimension. I'll come in here, select my line segment, and end up with 32.4 for the value here. And so 32.4 should match up pretty favorably with the value from the hand calcs. So if I go to the hand calcs here, and I'll go back to analytical, you see we're at 32.62 here. So pretty good agreement there. Some of the error there probably comes from approximating the velocity here, 6 pi. On the other side, I kept everything as absolute as possible. and didn't make any approximations there, and so that is going to add to a little bit of this error that we're seeing between the disagreement there. But as far as after measuring this value, the linear velocity of c is 32.4. All one has to do is basically repeat the steps in the analytical solution. And so here we'd be at the exact same picture as you see before you. We know that the magnitude of v sub c is 32.4. We did get the same direction there, upward and to the left. And so we would be thinking the same thing here. V sub c is equal to L4 omega 4, except for if we followed strictly what we just did, this number on the numerator would be 32.40 instead of our 32.62 there. But it should come up with a very negligible difference to our angular velocity of the rocker. And so even though this is a largely graphical solution, there would have been a little bit of hand calculations you could see at the beginning in order to get the length of this line segment to represent the linear velocity of point B, as well as to go from the linear velocity of C, which we measured, to the angular velocity of the given length. And so again, one of the things to focus on is basically just think of the relative velocity equation to pick out your points, and then also just really focus in on the vector addition. In my mind, I always think tip to tail addition there in order to work that vector equation out graphically, and then you can then just measure the lengths of your line segments representing the vector magnitudes. And so thank you for watching the video.